Welcome to a lesson with Dr. Powell. Let's take a look at an example of Riemann sums. So adding up rectangles. Now, when we make a rectangle on an interval here, we want these rectangles to fill up the interval. So if we're approximating the area under the curve of y equals x squared on the interval from 0 to 1, we need these rectangles filling out from 0 to 1. Now, it's common practice to make all the rectangles have the exact same width. So here I'm using 4 rectangles, so I just split up 1 into 4 parts. So I take the total length, which is 1 divided by 4, so each one is 1/4 width, has a width of 1/4. Next, how do I decide on the height? Well, there's various ways. Honestly, for a Riemann sum to work, really all we need to do is just look at this interval and just go up at some point. Doesn't matter where we go up. Here, 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 at the end, there. And we just need to hit the function somewhere on the interval and then go across. Any of these rectangles would work as a Riemann sum. So in this particular case, I'm using a rule where I always go to the right end of the little subinterval and go up and then over. Go to the right end, up, over. Right end, up, over. Here is an example of doing it on the left side. There, here I go to the left, here I go to the left, here I go to the left, and I have this. So this particular case, so this would be considered a right-hand sum and a left-hand sum. In another video, I'll give an example where we go in the middle. Okay, now this. So then what do? We just compute the areas of each rectangle individually. One nice way of doing this is to think, well, it's going to be width times height plus width times height plus width times height plus width times height. But if the width I've standardized to be the same, I can just factor that width out, and it really just amounts to multiplying width times the sum as a quantity of the heights. So I can just kind of think of the heights. And since I'm going on the right end of each subinterval here, let's think. I go to 1/4, I plug 1/4 into the function here, square it, so I get 1/16. So that would be the height of this first rectangle using a right-hand sum. For the next one, I plug in 1/2 into the function to get 1/4. So that's my next height. Then I go over to the next subinterval here. Go to the right side, I have 3/4, plug it in to the function, get 9/16. Here, have 1, plug it into the function, get 1, add these up, multiply, get 15/32. Do a similar thing for a left-hand sum, where I'm plugging in the left-hand side, left part each time, 0, then 1/4, 1/2, 3/4. So I only go to, so here I'm plugging in, for the left-hand sum, we are just plugging in 0, 1/4, 1/2, 3/4. Just these guys. For the left-hand sum, or for the right-hand sum, it's like we're plugging in these points here. So really, if you just get the end points of all the little subintervals for the rectangles, for a right-hand sum, you just take the, you just eliminate the first guy. For a left-hand sum, you just eliminate the last guy, and basically just plug in, get all the y values, multiply by the common width, and there's your approximation. Over here similarly so then we get both of these approximations. Now notice that the left-hand sum approximation is an underestimate, since all the rectangles are below the curve. And this one, the right-hand sum, is an overestimate, and for the actual sum, so the rectangles kind of sit above the curve. The actual we can compute by taking the definite integral and actually seeing what it is, and we end up getting 1/3. Notice that 1/3 is between these. This is below it and this is above it, just as expected. Thanks for watching.